Advanced Science and Technology at University of
Sorry.
Illinois Urbana. So, no, you're good. Just down the road from me with Jose Mestre. Am I pronouncing that correctly?
Yeah, mystery. Yeah.
Mestre. And in 2020, they co-authored a book entitled The Science of Learning Physics, Cognitive Strategies for Improving Instruction. This is her 15th year teaching at UWL, involved in several national efforts, including the PhysTech, Physics Teacher Education Coalition, Get the Facts Out about STEM teacher recruitment, and the Council of Undergraduate Research. And she lives at a hobby farm in southeast Minnesota with her mathematician husband, two boys, horses, chickens, barns, cats, and a dog. So quite the collection. So yeah, so I'll stop sharing my screen and I'll just turn it over to Dr. Jennifer.
All right. I'll make sure. I think.
Yep,
All right.
looks good.
So, yeah, I'm a busy person, but um, this is good because it's been a while since I thought about my dissertation research. So this forced me to kind of go back and look at it again. Um, oh, now I got to figure out how to advance my own slides. There we go. So as Anthony said, I'm originally from North Dakota, so I was thinking that I would want to teach high school physics. And so when I was in college at NDSU, I was a physics major, but I was also going through their teacher preparation program. And as I was just about to go into student teaching, a lot of my friends were applying to graduate school. It was sort of that November, December time. Some of my professors were like, "Have you thought about going to grad school?" And I was like, "No, what's that?" And one of my professors had attended the University of Minnesota and told me they have this thing called physics education there. You should check it out. And I was like, "Oh, that sounds interesting." So I kind of applied to grad school on a whim. I didn't really apply that many places because I thought I was going to be a teacher. And it really worked out in my favor. I think I really enjoyed it. I ended up getting into the program, obviously. But I went there specifically because I wanted to do physics education research. So I got the, master's in high energy physics on the way, but I really knew I was interested in physics education research. So I was there from 2004 to 2009. That's when I finished my PhD. And then I went on and did a postdoc with Jose Mestre, and it was in cognitive science. I was really still kind of interested in how the brain works and stuff. And so that was also a very fruitful collaboration. And we ended up writing a paper that is sort of a synthesis of discipline-based education research. And later on, we wrote a book together. And so I was really interested in this new stuff I was working on. And so it took a long time to publish the research from my dissertation about the maps. So there is a paper that came out in 2016 about the Minnesota assessment of problem solving rubric, but it took a while because I was really distracted by new and interesting things and not as interested in my dissertation research after finishing that project. So, but I'll share more about but now it has been at least 15 to 20 years since I've really done a lot of this research. But I came to UWL, University of Wisconsin La Crosse in 2011. And so I've been here for a while now. I became department chair last year. But in all honesty, I still struggle with this. Like, how do I design my courses? Um, how do I teach problem solving to my students? Like this semester, I'm teaching our introductory calculus-based physics, and at La Crosse, it's about 40 to 50 students in that class. We don't have a big engineering program here. So I was thinking, oh, like maybe I'll collect homework this semester. And now I'm like not sure if that was the best decision because it's a lot of my time to grade homework. They hand in like written papers of homework and I try to give them feedback and stuff. But I really am trying to emphasize like good problem solving practices to my students and trying to give them, feedback that reinforces those strategies. So, but I'm still like every semester, I'm like, I don't know. I still feel like there's so many decisions in teaching and so I'm still figuring this out too, even after all this. And I also think that things are constantly changing. So, we've had online solutions for quite a while, but now with AI and generative AI, students are kind of changing their approaches to learning and the way that they approach learning physics. And when they come to my office hours to ask questions, usually they tell me, like, well, I tried to look it up online, but I didn't quite understand it. So, can you walk me through this? So, they're already looking at other resources before they come talk to me a lot of the times. And I think it's different now than it used to be. So, um, I'm going to kind of talk a little bit about what I did in developing this Minnesota assessment of problem solving. So, I still really think that problem solving is an important goal of our physics classes. Like a lot of departments that we serve, is that we have a lot of pre-health majors in our classes. Like part of the reason they want students to take physics is to develop problem solving skills, whatever they mean by that, but they want them to think through problems and learn how to solve problems. And so, uh, I think we need some kind of the focus of the dissertation research was really to develop some kind of instrument that was more standardized to assess problem solving, to assess students' written solutions to physics problems. If you go to the Phys-Port website where they talk about a lot of resources from physics education research, they have an assessment section and they have tons and tons of stuff about conceptual learning in physics, the force concept inventory, all of these different assessment instruments. They have tons and tons of stuff on conceptual understanding, but trying to find something on problem solving, I looked at it the other day, there's like three. and and one of them is just like a paper that kind of talks about their in Colorado they did some research on what we mean by problem solving skills, and it's not really an assessment per se. And then there's a um, one that was developed quite a while ago, but wasn't really published. So this is kind of an area where there isn't a lot of information, like how do we really assess problem solving? And we wanted to have something that, could apply to a wide variety of different topics in physics and different types of problems. And, maybe it shouldn't depend on how the instructor is teaching. Like there are a lot of frameworks out there, a lot of research on like giving students a specific set of things that they should include in their problem solutions. But we wanted this assessment instrument or this rubric to be sort of very general that could be applied in a wide variety of situations. So when you develop an instrument, you have to go through some standards for reliability and validity. So I'm not going to bore you with all the details on that. If you want to read my dissertation, you can look more detail on that. But we really had to do a lot of testing of like different people trying to use the rubric to see if there was some reliability in their scoring, and then develop some training materials to try and see if we could get high reliability between multiple people using it. Validity, there's a lot of different sources for validity evidence. I'll talk a little bit today about the theoretical foundations of the rubric and how we used existing literature on problem solving to develop that. But then we had to collect a lot of other evidence um, just related to, we did interviews with students to see, if their written solutions were consistent with what they were thinking about and stuff. So we did a lot of different scorings and tests um, over like 2.5 years. And the rubric went through at least 8 different versions. So there was a lot of stuff that went into it and went into its development and testing. So if you ask what is problem solving, there are some resources and some definitions that you can find if you just ask what is problem solving. One way of thinking about it is it's a process of moving toward a goal when the path to that goal is uncertain. Some researchers describe like maybe there's a gap from where you are to where you want to be, and problem solving is finding a way to cross that gap. But it's also important to note that what might be a problem for one person maybe isn't technically a problem for another person, because it should involve some decision making. If you look at a problem and you know immediately how to solve it, that's what the literature would call an exercise. Like you already know the steps of what you need to do. It's not truly a problem for you anymore. So those of us who have been teaching for a while and we're looking at doing an introductory physics problem that we've done a million times before, that's not really a problem to us. But our students who are learning it for the first time, they might see it as a problem because they don't always know exactly what they need to do. So there's a little book by Poya from the like 1940s. It's a really old book about how to solve it. And so this definition of the problem solving process is used quite a bit in the literature. That first you have to understand the problem, make a plan, carry out that plan, and then look back and see if you really did solve the question that you set out to solve. And there's feedback loops in here. Sometimes maybe in the process of looking back, you realize that you need to come up with a new plan and try something else. So this is just one way to think about it. When we apply this general problem solving process in physics, you can think about, maybe you're trying to sort of organize the problem information, try and understand the problem, what's going on, identify maybe some of the key concepts, and then make a plan. How am I going to get from where I'm at to where I want to be in this problem? The carrying out the plan is oftentimes mathematics. And then looking back, students don't always do this. We don't always practice this all the time, but try to ask yourself at the end, does this make sense? Did I actually answer the question that I was trying to answer? So when we developed the rubric, we were thinking about this definition of problem solving, the problem solving process, and how it applies to physics. And then there were a lot of other people who did their PhD work at Minnesota before me who had also done work on problem solving. So a couple of them are listed on this slide, but like Jennifer Blue, Tom Foster, Tom Thaden Cook, and even some of the research by Pat and Ken Heller when they were doing cooperative group problem solving, they also thought about how we assess problem solving in that process too. So we took all of this information and came up with some different categories. And then, and so this is just a description of each of these categories. And then I'll talk about a little bit of the resources behind it on the next slide. So like I talked about on the previous slide too, the useful description is more like organizing information from the problem. Maybe it's writing down what you're given and what you're trying to find, assigning symbols for quantities. Maybe it's drawing a picture. Maybe it's drawing a free body diagram. There are a lot of things that can go into your description of the problem. And then choosing an appropriate physics concept or principle, applying it to the specific situation that you have in the question, and then following, carrying out your plan, I guess, following the math procedures. And then logical progression is something that, experts do. I guess they have a more coherent solution. It's not necessarily a linear solution, but it is consistent with itself. So you don't see like inconsistencies within the solution. So this is one of those things that's a little bit harder to define, but you know it when you see it. So you can tell if I'm great, like looking at a student's solution, if I can, read it and understand what they're doing, it has good logical progression. If it's sort of all over the place and you're trying to figure out, you spend a lot of time trying to figure out what they're doing, it's probably not very good logical progression. All right. So this was also based on research on what experts do when they solve problems. So there was a lot of research in the 80s about problem solving in physics. And what experts do is that when they read a problem, they first kind of do a qualitative analysis or a basic description. So that went into what we call the useful description. And they start with principles. They say, do I think this is a conservation of energy question? Do I think this is a forces question? What is going to be my general approach? Oftentimes students who aren't very experienced in physics will start with equations and they'll try to match the symbols or something in the question with an equation. Or they might cue on some kind of surface feature like an inclined plane or a pulley, something like that. So there are some differences in the way that more experienced people would approach solving a problem. And there's also differences in the way our knowledge is organized. So when a more experienced person is solving a problem, our knowledge is chunked in our brain. So when we kind of try to identify what principle we're going to use, then we say, okay, now we have this procedure or these strategies for that particular type of problem. So we can apply then those procedures after we've identified what is the principle I'm talking about here. And then, sort of executing the plan. And what experts do in terms of the logic piece of it is they plan and they monitor their progress. If something seems like it's not quite going well or they're getting a weird result, they'll go back and say, well, maybe I need to try something different. So that sort of monitoring piece or the the cognitive pieces that are going on there is what experts do. So the rubric I talked about, then sort of these different categories, and then we went through multiple different versions with, I was just looking at an older version of the rubric that only had points up to 4 instead of 5. So I think uh, it went through multiple iterations, but we ended up with this sort of scoring scheme in the rubric. So if something was missing or there was no evidence, we would put a 0. If everything, they had stuff there, but none of it really was appropriate to the problem, it would be a 1. And so then it's kind of like if everything was appropriate, it was a 5. If there's minor things or some or parts are missing, I think when we had only 4 points, people they wanted to have a middle point. They wanted to have a 3 and then think about, is it above a 3 or below a 3? So I think that's why we ended up expanding it to 5. And then after some of the work we did with graduate students and TAs, a lot of them really thought like, well, sometimes maybe a piece of this isn't necessary for a solver. So maybe they didn't have to draw a picture. Maybe they didn't need a description, but they were able to solve the question. So that some of these are more of a judgment call. Like, do I think this solver really needed to engage in this process or not? And then sometimes there are problem characteristics that influence the way you apply the rubric too. So if you write a problem and the picture's given, and there was no additional description needed from the solver, then maybe you would say that was not applicable to this problem. If you say in the problem, use the conservation of energy approach, then maybe they didn't have to make that physics approach decision. So when you write a problem that takes out pieces of the decision making process, then maybe it's not applicable to that particular problem. So we were trying to make the rubric general enough that it could apply to a wide range of problems. We tested it with textbook solutions, which are typically pretty sparse, and we also tested them with more detailed solutions. This is what it looks like. You don't need to like necessarily read it all through, but just notice that we had our 5 different pieces of the problem solving process, and then we have the different ways that we're scoring it. So in general, everything complete, you get a 5. If there are a few minor things missing, it would be a 4, um, down to 0 or not applicable. All right. Are there any questions at this point? And then we'll do some examples.
Don't see any questions in the chat. I just had a quick question. Uh, the students have access to the rubric, like they know kind of how they're being assessed prior to like attempting a problem.
When we designed the rubric, we were primarily using it for research purposes. So we didn't like actually test if we had students look at be aware of the rubric or know how they were being assessed. So when we were developing the rubric, we didn't actually do any studies like that in a classroom where we told students ahead of time how they were being assessed. We just collected solutions from exams, like photocopied exams, and tried applying the rubric to that. Um, I would say at the University of Minnesota, a lot of people use cooperative group problem solving with context-rich problems. So some of the students are like following a bit of a framework, but other instructors don't use it. So it wasn't always consistent. So in this particular study that I did for my dissertation, like the students were not aware of the rubric or how they were being assessed.
Gotcha. Thanks. And Yawin, do you have a question?
Yeah, I actually have two questions. So I'm just thinking, because as a grader, when I look at the rubric, I would feel like it's kind of a lot to like
Hmm.
pick. So have you considered like 3 instead of 5 points? And another thing is you mentioned about the group work, group problem solving. Yeah, like how does it work out? Like, do you do the group and then break it down to individual, or do you do like reverse, and how does it work? But I don't know if that's kind of detour from what you're talking about, but that's my two
No,
questions.
I do have a slide later on about, and we talk about this in our paper a little bit too, about like using this for research purposes versus using this for in a classroom for grading students. So when we were developing it, we were kind of thinking about it from a research perspective because in that case, it's useful to have 5 points, the same number of points for every category. Um, and you want to be able to compare across maybe instructors or different classes or somebody, you're testing out a new instructional technique and you want to see if there were aspects of the rubric that showed improvement for your students. So if you're actually going to use it in a class, I think you would maybe want to weight some of the categories differently. So maybe like in my class, when I give exams, the problem part is usually like each problem is worth 10 points. And so maybe I give 1 or 2 points for the description. The approach is maybe 2 to 3 points. Specific application is 3 points. So even in talking to the graduate students when we were testing this out, they wanted to give most of the points for the physics aspect of the problem. Um, Math procedures, maybe I take off a half a point or a point if they make a mistake in the math, but it's not a ton of the points. And then logical progression it sort of comes out more in being able to communicate their reasoning. So I think I don't know if maybe that would be like 2 points or something like that. So if you're thinking about applying this to um, you would want to do weighting, I think. So you would want to maybe put more weight on these categories. So this is assuming like you're just scoring 5 points for each of these, which would be 25 points, which kind of seems like a lot for a problem too. But what you can do with it if you're scoring on for research purposes, I think that makes a little bit more sense to have a comparison, a consistent way to compare across different problems or instructional approaches. So when you think about this in terms of grading, maybe you think about it more in terms of what kinds of things you're looking for in a quality of a student solution and thinking about maybe the points would vary based on the kind of problem you have. So the rubric itself was more for a research application, but I think if you were to sort of weight the categories based on what you think is most important for that problem, you could use it for grading. In terms of like doing cooperative group problem solving versus individual problem solving, my students do group quizzes and I look for very similar things when they hand in one paper for their group. Um, I think you just have to think about what's going to be most important for the problem that I'm having them solve.
Thank you.
All right, well, maybe we'll look at this was one of the problems that we used early on in our scoring. And so I'll give you a moment here to read through this question. And as you're reading it, maybe think about your own thought process and how are you trying to classify this problem and think about this problem. All right, so if anyone's willing to share what's going through your mind as you read this physics question. Or you can put it in the chat if you don't want to say it.
Yeah, I'll agree with Paul, like a kind of before and after picture for conservation of energy.
Okay.
I think before
I came to conservation of energy, I was debating, right, as I'm reading the question, you know, is this going to be a spring or oscillation type question? Is this going to be a kinematics question? Is it going to be an energy problem? So I was thinking about those things first. And in the chat, someone asked if they raised the money, and there are too many deans.
Yeah. I know, right? But this is an example, I think, Minnesota, they try to make what they call context-rich problems. So they try to make it more of a story. I mean, I don't know if this was based on a real story or not, but but in any case, so we're trying to use clues in the problem, like, oh, so there's a spring. What do I know about springs? I could either go in an oscillation approach, a more forces approach, or it could be energy. Like I know there's there's potential energy stored in that spring too, elastic potential energy. So, but if you're an experienced solver, someone who is pretty familiar with physics, you're also trying to classify it based on the principle that you're going to use, conservation of energy. So students might not always think about that. They're probably cueing more on the fact that there's a spring in this question, but that's how we're thinking about it as a conservation of energy question. I'll also point out that in here it says that you're in free fall for 30 meters before the cord begins to stretch. And so you'll see in some of the student solutions, like they think that that means they need to use kinematics and free fall for that first part, when actually you could just use conservation of energy without having to do anything with kinematics. So these words, they do, the students do kind of cue on what's going on in the problem and affects the way that they're going to approach the problem. All right, so I have a couple samples here and this is the instructor solution. So this was, what we were talking about. You have maybe a description for the initial situation. So first you have to find the spring constant K in part A. And so you can do that directly using the initial gravitational potential energy, setting that equal to the elastic potential energy in the spring, and then solve for K and get 400 newtons per meter. In the second part, there's conservation of energy again, but now the spring is not fully stretched. So you're going to be 7 meters above the water, and so the spring is partially stretched, like 5 of the 12 meters. It still has some velocity and it has height above the water. So we'll see that sometimes students, they miss this like height above the water, or they're missing, they use the wrong value for the stretch or something. So the students, maybe they know to use energy, but they still make some mistakes in the specific application to this problem. All right, so we'll look at uh, in light of that, we'll look at a couple examples. All right. So I'll give you a minute to kind of look at this. I don't know if you can hear the chimes. It's like the chimes. There's a clock tower right outside my window. So what do you think we would want to see in a description for this question? Anybody have thoughts about this description? Would you like to see more? Is this one sufficient?
I mean, I guess personally, just because of when I teach this, we kind of follow a specific framework in terms of like nodes and unknowns and things like that. So I guess depending on what has been modeled for them, this could be fine. I guess for me, usually I'm pretty rigid in terms of like, oh yeah, identify your nodes and unknowns, and like for this, like kind of a before and after picture is something I'd be looking for.
I like that there is a picture, that there is a drawing, and That seems pretty key. Or that would seem problematic if it was missing.
Hmm.
Not
So
that there couldn't be
they have
more.
something, right? They
Yeah,
have something there, which is better than nothing.
right.
I would love to see like that first 30 meters free fall, and then the next 30 meters, a comment that said something like free fall, and then a spring stretch. Just something that describes what's going on in a verbal way. I
Hmm.
think we lose that too often in our problem solutions. Everybody wants the number, but a description is oftentimes not part of it.
I was just going to say I'm impressed that the student put like a coordinate axis at this late stage. Usually that's something that they like give up on.
Yeah. Yeah, so there are some good things here, but I would say too, like I would like to see more, like more description maybe about what are we talking about for the 42 meters or the 30 and the 12 and yeah, I mean really what's going on in terms of the stretch of the spring and stuff. And maybe a list of givens and what you're trying to find. So, I mean, on in terms of a rubric scale from 0 to 5, maybe a 3. I don't know. Like I think it's kind of in there. There's something there, but parts of it are missing. So that's kind of what I would call a level 3. Or maybe you put it down to a 2 if you really felt like it should have had more in there. So what do you think? The next piece would be to think about the overall physics approach that they used. So what evidence do you see on the paper of their approach?
They thought about both kinematics and conservation of energy, and they actually wrote out conservation of energy, which I
Mhm.
thought was appreciated, although it seems like they were incorrect in some of how they did things.
The one thing I like to see with conservation of energy is always tell them to write like the full equation for conservation
Mhm.
of energy and then consider each one. Like, is there initial potential, initial kinetic, external work? And then they look at each one instead of just it goes from kinetic energy theorem. They disregard some sources of energy, but they always start with the same one, whether we're dealing with rotation or linear kinematics or there's friction, like they would really have to think about where all the energy is going.
Yeah, and in my class too, that's we have an equation in the textbook that's like K plus U plus work by non-conservative forces is equal to K plus K final plus U final. And so, yeah, I do tell them to try to map it specifically so I know, are you talking about potential energy here, kinetic energy, what's going on? So maybe a little bit more in terms of a general equation before a specific equation could be a useful thing.
So uh, when they took this test, they had already gone through a few tests where the grading had already been, described for them. So they would know what to expect at this point, right? Because I'm assuming this is kind of like two-thirds into the semester or halfway through the semester.
Yeah, so this was a calculus-based physics class at the University of Minnesota, like their physics for scientists and engineers. But this,
Right.
they have cumulative final exams. So this was on a problem that was on their final exam.
Oh, so they had
So
already gone. Yeah.
yeah, um,
So in that case, I would say something is missing because if it was the first time that they were taking a test and they didn't know they were supposed to put this and that comment, I mean, in the solution, and then you said, well, that's why you didn't get full credit. That could be a bit of a problem. But if it's on the final, that's different. Yeah, yeah, they've gone through the whole semester already at that point.
yeah. So if you were going to apply the rubric here and kind of score their approach, um, I mean, conservation of energy is an appropriate principle to apply in this situation, but maybe there's minor omissions there that we would have liked to see. So maybe that's more of a 4 out of 5 or something like that on the approach. In the specific application, when they do part B, they are missing like a part of the gravitational potential energy at the end. So they are missing a piece. So that would probably be a deduction that happens in the specific application of the physics. And if you're paying attention here, like they're supposed to be solving for k, and they take the square root of both sides, and there's some strange math stuff that goes on there too. So this is an example where maybe they made some strange, mathematical things, mistakes in there too.
I would use this as a poster child, not the student himself, but one of the things that I stress, and this goes back to the last step, looking back, is if you worked out the mathematics on that top line, the k equals, and you put units in there, and that's my students are going to call me like Mr. Units because I want those units inside of that equation. And if they did that, they would find that they don't get newtons per meter because they have the incorrect units or the incorrect algebra, right? And that's a great way for them to see, man, I made a mistake someplace. And this student would be able to identify that. Now, whether they have time to fix it is a whole nother story. But I'll actually give credit to my students if they wrote off to the side, I have a unit problem. And then they move on to the next problem. I'll give them part of that rubric. If you had looking back as part of the rubric, I would give them points for that because they would have realized that they had a unit error in that square root. And I find that to be super important, especially for the looking back aspect of problem solving.
Thanks. Yeah, that's a really good comment about um, including units and checking your units in that final answer.
I wanted to add two things to that. I do also tell my students, besides the units, I do tell them like units at every step because you will catch mistakes, and it's important for the field you're going into. Like if you just tell them like how much force can this bridge support, it's like 20. It's like 20 what? It's got to be something. So it's I keep emphasizing it whenever they ask like is this correct? I'm like it's missing something. It's like it's missing my second favorite thing, and then they're like, oh, units every time. But also if they do notice a mistake in the problem and they write like I know this is completely wrong, this answer makes no sense, like that's something that they're actually thinking about what they got. And I'm like I always tell them like it's worth something. Just think about your answer.
One thing I would give kudos to, and it kind of goes back to what Dan was saying too, is including units in the problems. But what I love that this student has done is she or he did everything in variables, and the numbers didn't go in until the very end. And like Dan was suggesting, you put the units in at that point in time, and man, you are flying right now where you want to be. That would be awesome. But I love that there are no numbers until the very end.
Yeah, and that's something we discussed quite a bit when we were developing the rubric too, is that that is a preference, I think, among most people who are teaching physics. They really like to see the numbers in the last step. The students don't like to do that all the time because they think it's harder algebraically. But I think that contributes to the logical progression. So if you can follow what they're doing in the symbols before they plug in the numbers, that makes it a lot easier to follow their work if they're waiting to put in the numbers until the last step. So I think that is something that we're not scoring for explicitly, but it does contribute to a more logical solution. All right, let's look at another one and kind of see what you think. So I think this description is kind of similar to the last description we saw in terms of kind of minimalist. Okay, I'm seeing some people say in the chat much harder to follow. I know everyone looks very serious, like, what are they doing? What are they trying to figure it out? I'm the same way. I'm like, I'm not quite sure what's going on. That's why there's a question mark there. And maybe they are kind of fixated on the kinematics side of things rather than thinking about energy.
And I think both cases is, I think they will make it much easier to follow if they state specifically where is the initial point, where is the final point they are considering. Like, I think both students don't have that, and then it kind of makes it hard. Like, what do you mean by I? What do you mean by F? Yeah.
Mm-hmm.
If you look at the diagram and then that left-hand set of equations, you've got that the spring force equals weight, which assumes that there's no acceleration. They do label that the velocity is equal to zero at the bottom. And so I think this student has not yet perfected the idea of velocity is not acceleration. Even though they solve for the acceleration on the right, the left-hand equation assumes there's no acceleration if the force of the spring equals weight.
Mm-hmm.
But there is.
I'd put this in the chat, but I'll also say that it seems like neither student used their coordinate system. I'm not sure this one has one, and the other one put one. The other solution they wrote as a coordinate system, but it didn't seem consistent. Everything was downwards, and so there should have been some negatives. That didn't seem to work out.
Yeah, so some really good observations about, thinking about the approach that the student is taking, and maybe it's not appropriate for the situation for some particular reasons, or maybe they're not applying the approach that they chose in an appropriate way. We found when we were testing it out with graduate students too, if the students had a completely like inappropriate approach, they didn't even want to grade the specific application. They wanted to just say like it's just wrong. And so sometimes those were kind of tied to each other. I think that people, if they didn't really have a correct approach, it was hard to think about did they apply an approach in appropriate ways. So that was the conversation we had a lot too. And so this one, yeah, it's a little bit harder to follow. And there were quite a number of students who tried to use like KX is equal to MG. So I don't think that was an uncommon approach too. All right, so I think maybe we'll do like one more and then I'll take questions, some time for questions or additional discussion.
The logical flow kind of bothers me when you see like symbols that sort of appear that don't follow from the first step. Or from
Yeah,
earlier
and I think
steps.
that's like, okay, they wrote this down, but then is this something different or yeah, I agree. I'm trying to understand what's going on here and then where things are coming from. And there's a square root of a square root. We don't see that very often in physics either.
And energy, is that a thing in physics? Never heard of it. Especially at the end of the semester. Well, okay. It's like the semester stopped at kinematics chapter, right? Nothing after that registered.
they're applying kinematics when it doesn't apply. It's great
Yeah,
for the first 30 meters, but after that, it's not.
yeah,
And that
yeah.
in the diagram, since we're talking about the diagram doesn't show that there's two parts. At
Right.
least in the other two, they showed two parts to the problem. One when the string or the rope was not stretching, and then when it did. But this one doesn't even do that.
So they took the time to draw the crane and everything, but they didn't have the important information on that diagram. I don't know. I see that in my students sometimes too.
You need a quality of drawing category or something.
Yeah. Well, it is called useful description. Did they
Okay,
write
yeah,
a
I guess.
description that is actually useful for solving the problem or not? So,
Yeah, I guess. Yeah.
all
Well,
right.
if
So,
you look at the diagram, the description is misleading, right? Because
Mm.
it's not really telling you about the stretch or anything in there.
mhm. Yeah. Yeah. And I mean, there was just such a range. I think this is why we chose to look at this problem in our initial development of the rubric too, is that there was just a wide range of student approaches to this problem and just a lot of different things going on in terms of the descriptions and things. So there are some examples where people did do a little bit more with describing their approach, but they still made some, mistakes in the application and things. So there was just a wide range of solutions to this particular problem on a final exam. All right, so um, as I mentioned before, like we primarily designed this for research purposes, but I think it does have application to instruction too. Just for the purposes of grading, maybe you would want to think about how you would weight the different pieces of it. Like maybe you give more weighting to the approach and application of physics than you would to the description or math. If the description is really important to you, maybe you give more points for having a description. All right, so we had developed this specifically for uh, having a more standardized way to assess students' written solutions to physics questions. It was based on some of the earlier literature on problem solving, also work that other people had done at the University of Minnesota before me. We defined these 5 categories based on what experts do in solving problems. But you can kind of tell that it works better for more complex problems. Like if you have a really straightforward question that's pretty short, it doesn't really make sense to apply that to those kinds of questions. And if you have a lot of decision making, it's easier to apply the rubric too. So if you're already providing a picture, already telling them draw a free body diagram or something like that, then maybe the students don't have to engage in that process, and it may not make sense to score that piece of it. And so I think if you are going to use it more in a class, we didn't actually test that. So we didn't, and when I developed the rubric, we didn't actually test it out in a class. This was just sort of after the fact. We looked at some of the final exam papers to test out the rubric and develop it. So I think that maybe more research still needs to be done on this and how you actually provide it to students and see how they score on the rubric and stuff like that. So I think the classroom application we didn't focus as much on when I was working on my dissertation research, but I think it still has some applications to instruction and the way that we assess students in their written problem solving. All right.
I got a quick question. When you tested the rubric, did you find a lot of consistency among the graders, or was that kind of broad enough that they would be almost maybe not totally opposite results, but very diverging grading?
Yeah, we did a variety of different tests of the consistency in the graders.
Hmm.
And yeah, we did find, like, we looked at something that was like a Cohen's weighted kappa. And so Cohen's weighted kappa looks at if you are within like one of each other. So you didn't have to have exact agreement necessarily, but if you had close agreement, and it gives you a measure of like how close you were in your agreement. So we found that it took a little bit of training. Like people had to score, I don't remember, we had a number, maybe it was like 40 solutions, I think, before they were really consistent with each other. So you had to kind of come to some consensus or some agreement about how you were interpreting the categories if two people were using the same rubric. And so we did try to develop some like training materials, and we were used them with graduate students. The University of Minnesota PER site has some of those training materials that we used with TAs and graders to test that out. But they had to practice it a little bit first and come to some consensus about how they were interpreting these categories. But after that, we did get pretty good consistency.
And I'm not sure if you measured this, but how much time would it take for someone to become sort of comfortable or be able to grade at a relatively good pace with this? Because it seems like initially it would be very slow because you'd have to maybe think a lot about each weight and categories and you, I guess at some point become very expert in grading this, but how long does it take to get to that level of expertise?
Yeah, that's a good question. I think that if you're just thinking about it broadly as like, I'm looking for these five things, and am I going to score it? How am I going to, think about it in this range of
Yeah,
those, these five things, and not get caught up on there's so many boxes in the rubric,
yeah,
but kind of thinking about I'm looking for the approach, or I'm looking for the description, like how is the student doing on that particular area? And then, but yeah, I don't quite remember if we had like, uh, if we had figured that out when I did my dissertation research. It's been a while. I don't remember if we
yeah.
said like, oh, how
Okay.
long does it take to actually get proficient at using it or applying it? But
Yeah,
now that I'm, grading homework and stuff for my own classes, I like to think about it more as like a point system that's a little bit smaller points than five for each category. And I usually think about, okay, what am I looking for in the description? How many points is it worth? What am I looking for in their general approach and their specific application of their approach? So you may do some of this already when you're looking at student solution. This is just maybe giving it a name to some of those things that you're actually looking for in the solution.
Kind of following up on the consistency in the rubric. Um, have you done anything to see if by using a consistent rubric, have there been any variations between student success in the problem solving process when you've altered the way the class is taught? And real quickly, I when I did my dissertation, I taught using a flipped classroom, but my control instructor just used a standard lecture format. But we got together and we designed the rubric. Definitely not as nice as yours, but we designed a rubric to grade our problems so that we were consistent, so that I could find out, is the flipped classroom giving me different results? So is that something you've done? And have you found anything that said this way is teaching is better than another, especially with physics?
Yeah, the short answer is no. I think we didn't do something exactly like that. I mean, I think we did score problems from two different instructors that they gave the same final exam question. I think I vaguely remember we did something like that. And we could see that the rubric was responsive to different instructional strategies. So if one group, for example, was required to follow a problem-solving framework while they were solving their problems, they may have scored higher on certain aspects of the rubric, and whereas the other class may have scored lower on certain aspects of the rubric. So when we reported things, we actually made bar charts of each of the categories. And so we could look at the average score, or I don't remember if it was like the frequency of students on each of those, like how many scored a three, how many scored a five, things like that. And so we could see in some of those situations that like, oh, well, this class did a lot better in identifying their physics approach than this class did, or maybe this group did a lot better on their description than this other class, because it was kind of responsive to, you could see that in the rubric if you had like results reported separately for each category of the rubric. And that's one of the benefits of a rubric is that you can kind of look at what were the strengths and weaknesses based on those five different categories if you're kind of averaging for each category separately. But I think there could be more research done on uh, using some kind of consistent problem-solving measure and looking at different instructional strategies and things, different implementations of research-based instructional strategies.
I think the other thing that would be interesting to measure was, maybe my class had a better score on the rubric than Ryan's class did, but did my students actually do the problems correctly with a larger number of higher scores than Ryan's class? That would be interesting to note whether that was also part of the process.
So since we're coming close to the end, I just want to first thank you, Jennifer, for this very interesting presentation, and also I don't know if I'll be able to do this. Oh, I guess, yeah. Sorry to kick off your sharing. Just put up the slide to get feedback for today's session. I've also put the link to the feedback survey here in the chat, along with links to the resources that Jennifer shared at the end of her slide. So yeah, I just don't want to necessarily cut off conversations. We still have a few minutes, but I just want to make sure I got that out of the way, and also get a chance to thank you for your time.
Well, thanks for having me. This is like I said, I haven't thought about my rubric in a while, but I think about problem solving a lot, not necessarily the dissertation research that I had.
So just to be clear, then you're saying that the rubric hasn't been used or in in classes at this point? I mean, since you published it, and just trying to find out if like somebody were to do it, that would be new information that no one has, right?
That's a good question. Yeah, I should look on on the physical
Yeah.
review, physics education research to see if somebody actually has implemented it. I guess I'm not sure if anybody has, but we didn't actually do it as part of our studies at the University of Minnesota.
Okay, because it sounds like a really interesting project to go through to see if we can, because we do a lot of, as you said earlier, we do a lot of conceptual, but not enough on the problem solving.